Agentic search is a very popular term right now, but this idea didn't appear overnight. Search has evolved over many decades to reach this point. In 1960s, for example, it's mainly about keywords. Later in 2010s, search shifted towards embeddings and semantic meaning. Then came hybrid search, which combined keyword with semantic search. In late 2020s, we saw RAG, a retrieval augmented generation. After that came deep research systems where complex query could trigger many follow-up searches to build a complete report. Now in 2026 we are talking about agentic search, and the key insight is this: the strong search is not just about vectors or ranking. What matters as much is the memory design behind the system, or the memory architecture. In this video I'm going to review a post by Hanzhao at Elastic to explain why memory architecture is so important for building these strong agent search systems. So first, where does memory come in? The most familiar version of memory is the context. When you chat with an agent, it works inside the context window. When you ask a query, agent may also pull information from external sources, from working memory and from long-term memory. All of that together becomes the context. So in that sense, memory is really a CRUD, what is familiar from web application, the CRUD problem. A system has to create, retrieve, update, delete information into the memory. Or more simply, the key operators are retrieve, update, and forget. And forgetting is the part that has received the least attention. But a useful model here is the Ebbinghaus forgetting curve. Basic idea is that memories fade over time. That's how memories work in our brain. Memories fade over time if they are not revisited. Only when they are reviewed over and over again, they become more stable and long term. And this idea has not been captured in agentic search. The retrieve and update operators are fine, but forgetting is not captured properly. And this matters a lot because time changes what is true and what is useful. A new piece of information can override an older one. So you don't need to just recall what memory. There are many ways to represent it. A useful starting point is the way we think about human memory: episodic, semantic, working parts, hippocampus, neocortex, prefrontal cortex. So this maps surprisingly well to agent systems. Working memory is similar to context window, and the information agent is actively using right now. Episodic memory is closer to vector database. It stores specific past events and interactions. And semantic memory is more like knowledge graph. It stores more stable concepts, takes longer to build entities and relationships. Problem is that many production systems ignore one or more of these memory types, and when that happens, the retrieval becomes weaker. The system may remember the immediate context but lose the long-term structure, may store facts but fail to connect them properly over the time. So like you mentioned, memory is a CRUD problem, and all of these components need to be paid attention to when building a retrieval system. So there are the four operators sound simple, but they have major consequences for search systems. Facts can become outdated or refined, and a system that only knows how to store and retrieve but now not how to forget, the answer will slowly become unreliable. So in terms of the memory architectures or infrastructure, there are three competing: graph-based, LLM native, or weights inside LLMs store the facts, and storage file system centric. Okay, so each of these has their own strengths and weaknesses. Memory inside the LLM weights is the most efficient to access. It can use it immediately, but the downside is that knowledge can get entangled with other memories, so it's very hard to update or to remove specific facts cleanly. The file system or the SQL databases give you a much cleaner separation from the LLM. They are easier for humans to inspect and manage also, but they create other problems like conflicting data can happen, or weaker retrieval, or less efficient queries because the indexes are not there. Graphs are quite powerful because they represent entities and relations directly. So many queries are directly about entities, and so graphs serves as the right infrastructure to answer those. But graphs are expensive to build and expensive to maintain incrementally, and often they are incomplete in practices. So there's no perfect memory format. Each one makes a different trade-off between speed, structure, clarity, and maintenance. LLMs have improved a lot over the last few years, and because of that, many approaches now lean towards keeping more information inside the model. The idea is simple: give a long context model. That's what they are called, a million token. They can handle context million token and above. So give the full knowledge base to the long context model, conversation query, the conversation history, and the user query, and hope that it can pull out the right facts from the right places of the context. But the results are not as strong as people expect. They've never been strong in spite of the large size. Long context LLMs can perform 30 to 60% worse in accuracy because they rely too much on what is stored in the internal weights instead of retrieving the right external facts. On harder queries, the problem is worse. The question that requires multi-hop reasoning. On these tasks, even best approaches top out at 39%. So the benchmarks are telling us something very important. Extracting a single fact is relatively easy. Fact which is there in one part of the document, one piece of the document, cleanly separated from others. And it's easy to extract that, but when the system has to reason across documents, across time, or across long conversations, retrieval and agent systems are still very weak. So recommender systems have been there for a long time. They have been optimized, and Hanzhao argues that recommender systems can make a comeback here because graph-based memory for agents looks very similar to personalization, what the recommender system have consciously paid attention to over a long time. There's some truth to that, but I think the agent memory is much harder problem. It has much more action space, a much bigger action space, far more complexity than simple patterns of user products and sessions. Agent memory has to handle much more diverse facts, relationships, and changing context. And recommenders also face the forgetting problem. They are not really built for forgetting. So to summarize, most vector and graph systems are good at narrow queries, but the temporal awareness is still weak. Systems still struggle to track how facts change over time, what should be forgotten, and how to answer multi-hop questions. One benchmark to watch here is long mem eval. On that benchmark, a system called Hindsight reaches a score of 91.4%. It has very unique architecture. It doesn't rely on a single memory layer. It has builds a hierarchy of abstractions over documents, chunks, moving from entities to observations to higher level mental models that include opinions and interpretation. It's a very interesting memory model that I'll cover in one of the later videos, and it performs very well on the hard long mem eval benchmark. So the bigger lesson here is that better agentic search may depend less on a single retrieval trick and more on designing the right memory hierarchy that can help answer different aspects of the query much more efficiently.